back. And so now let's assume that we've made our magma. Now the question is, why would the magma want to rise to the surface in the first place to make lava flows and volcanoes and igneous rocks? So why would it want to do that? Well, the first one is going to be buoyancy. And so this gets into the idea of density. And so in a previous lesson, we talked about what density was. And density is going to be the mass of something divided by the volume of something. And so we found out that, for example, oil is going to float on top of water because it's less dense. So for the same amount of mass, if you have the same amount of mass of oil and the same amount of mass of water, then what happens is the oil has more volume, and so it's going to have less density, and less dense things are going to float on top of more dense things. So let's now talk about magma. And magma is going to be hot, so it's going to have a larger volume. So just think of like a hot air balloon. If you heat up the air, the balloon is going to expand. So this magma, since it's very, very hot, is going to have a larger volume. And so if you put a larger volume in the bottom part of the formula, then what you get is a smaller density. And again, less dense things float on top of more dense things, so that magma is going to be less dense than the surrounding material around it. So it's going to want to float. So it's going to start to go up. So that's one reason why magma rises. Another reason why magma rises is it's under pressure. And so there are two kinds of pressure that are going to be affecting the magma. One is going to be the pressure caused by the rocks on top of it. So that weight, what it can do is it can squeeze the magma from all sides, and eventually that can force that magma up to the surface. Another kind of pressure, though, is that, let's say you've got a magma chamber, and then it's being fed from the asthenosphere down here. So as the material is coming from the asthenosphere into the magma chamber, it's putting pressure on it as new material is being injected into that magma chamber. So that magma wants to go somewhere because, again, it's under pressure. And so it's going to rise to the surface. What controls the rate that a magma then begins to cool off? So as the magma cools off, it's going to start to solidify into our igneous rocks and then into our igneous features like volcanoes. So what's going to control the rate at which that magma is going to cool off? Well, one is going to be conduction. So in a previous lesson, we talked about convection. We also talked about radiation was another way that heat can move. And then we talked that conduction was another way. And we said that conduction works the best in solids. So that this magma, as it's going up to the surface, is going to be surrounded by other rocks. And what those other rocks are going to do is they're going to conduct heat away from that magma. And so if that means the magma is going to cool down, and eventually it might get to the point at which it's going to start to solidify. Another thing is depth. So again, this gets back to conduction. So think about the difference between having a glass like this, and then you fill it up with hot water, and then you've got a thermos. So over here, you have something that has very thick walls to it, and you put your hot liquid in there. So which one is going to stay hotter longer? It's going to be the thermos. Okay, the walls here are very, very thin, which means it's easier for the heat to escape. The walls are very thick over here. Well, think about what it's like inside the earth. So the deeper you go inside the earth, the thicker it gets, the more distance that heat is going to have to travel in order to get to the surface. So that the shallower you are in the earth, the closer you are to the surface, the faster the heat can conduct through the crust. The deeper you get inside the earth, the slower things are going to cool off. And this is going to be really important because when we talk about textures of igneous rocks, we're going to see that some igneous rocks have very large crystals and other igneous rocks have very, very small crystals. And that's a clue as to where did they form. Did they form deep inside the earth or did they form near the surface of the earth? So just keep that in mind. Another one is the shape of the magma body. So things that have a large surface area are going to cool off faster than things that don't. So if you have a magma chamber that is spherical, then it's going to cool off slowly. If on the other hand you have another magma chamber that is shaped like this, even if this thing has the same volume as this thing, this is going to cool off faster than what this one will because it has a larger surface area. It's in contact with the surrounding rocks, which are going to conduct the heat away. And then it also depends on the size of the magma chamber. So the bigger the magma chamber, the larger the smaller its surface area to volume is. And again, the heat is just going to have a hard time traveling from the inside of the magma chamber to where you have the cool rock out here, as opposed to if you got a little magma chamber. Then the heat doesn't have to travel as far. So that your small magma chambers are going to cool off faster than your big ones are. All right, let's take a break, and when we come back, we're going to talk about why are there different kinds of magma.